Hi, I'm Nimish lad, and I'm here to talk to you about tricky ideas, specifically radioactive decay, why it's so hard for students to understand, and potential ideas to almost get around that. And one of the ways that I'm going to talk to you guys about it is using the idea of modelling. So what I'd suggest is, if you haven't seen my video previously on modelling techniques, where I refer to two of the examples that I'm going to use in this video, then please do go and watch that first. So I'm going to talk about why radioactive decay is so hard for students to understand, and actually for many teachers to actually understand what's going on, and how we can use the idea of Guinness to actually model it, and how we can actually use the idea of popcorn to model it as well. So why actually is radioactive decay so hard to understand? So I'm not talking about absorption. I'm not talking about alpha, beta, beta plus, beta minus, gamma, or neutron decay, and that process of what happens in terms of the atom, where a particle is given out, the mass number, the atomic number, proton number, the number of protons, neutrons, electrons, they all change within it. That's fairly straightforward. Once the maths of that is clear, students can do that. What I'm touching on here is more how is the process of decay over time modelled, which is really difficult for students to understand. So part of the reason why it's so difficult, sorry, I'll just go forward, is you can't see it directly. You can't see the particles leaving, you can't count the particles leaving. It's difficult to conceptually visualize what's going on. So you could use a Geiger-Müller counter and a protactinium generator, and take some numbers off there and put them on the board, and that's a great process. However, it's physically difficult to actually see what's going on there. The other thing that's difficult is that the rate of decay is directly proportional to how much remain. So that sounds like a really strange statement. So what that's getting at there is the rate at how quickly the number of particles are going to decay, so change from whatever they were before to what they become. The rate at which that happens is directly proportional to how many of those there are left. So if A becomes B, the rate at which A becomes B is directly proportional to how many of A there still are. So that's really difficult for students to understand. Even just explaining it then, it's tricky to get across in words. So there's really interesting ways of showing that using Guinness and popcorn that I mentioned. There's some really complex maths involved in this. Okay, so that idea of decay and it being exponential is really, really complex. You can draw the curve on the board and students can see the curve and say, okay, cool, that's great, I get it, it's not a straight line, it curves down. However, the maths behind that is complex. The idea of the exponentials, either growth or decay, is difficult for anyone to get their head around. And there's the idea of constant change. There's constant change in these systems. It's not that it's there's a set process that happens. Well, there is a set process that happens, but there's a constant change within it. That rate at which things are leaving is constantly changing. So what about the dice experiment? You might have come across, let's move this up here. You might have come across the dice experiment before, where students have a beaker full of 100 dice, let's say, and one side of the dice, if it's made of plastic blocks, and please do make them out of plastic blocks, don't buy 100 dice, 1 to 6 dice, because that will cost you a bit. If you get your DT department to cut up plastic blocks, 100 of them, and just put dots on one side of them, that's just as good. The idea is they roll them out, fill their beaker up with 100, they roll them out. Any one of them that comes up with the black dotted side up, that's decayed. You move those to a side, you keep the rest behind. You keep going, you keep a log of how many have decayed each time, how many are remaining. And what you can see is if you track how many are remaining, you end up with a nice exponential curve from this. That's great, but it's time consuming. Okay, it's not a quick experiment. It does take a lot of time, it eats into an explanation. What I'm getting at is it's not clearly guided. You can't explain while students are doing that experiment. There's a hell of a lot of noise going on. There's a lot of cognitive load. There's definitely split attention in the room if you're trying to talk over them while they're doing the experiment with the dice. So something to get into there, that although yes, it shows what's going on, you can't guide them through the process of how this model links to radioactive decay. It's messy, just dice everywhere, and it leads to messy explanations like I just discussed. It's difficult to manage, really difficult to manage in a classroom. You've got to make sure that everyone's at the same point if you want to try and get an explanation across as you're doing it. So I like to use this idea instead of Guinness instead when I'm solidifying the knowledge when it comes to radioactive decay. With a dice experiment, like I said, messy, difficult to manage. But this isn't. Yes, there might be a bit of silliness around the room when you get a can of Guinness out and pour it into a beaker, 100ml beaker, 250ml beaker, whatever you wish. But the key thing with it is that it allows you to go through the explanation step by step in terms of how this ties in with exponential decay. So the first thing to talk about is the head at the top of the Guinness. So as you pour it out so you get a decent head on the top of it. What happens is over time, the size of that head will decrease. And the rate at which that head decreases is directly proportional to the height of the head. Now, you don't need to sit there and take measurements with this. And this will happen relatively quickly within a minute or a minute and a half. You'll see the size of the head decreasing, and it's a situation that students will be fully aware of. They would have seen things like this before. So the idea is you can talk to them about the fact that when there is more head, that height's going to decrease quickly. And when there is less head, that's going to take a long time to decrease. And that is exactly how radioactive decay works. When there's more particles that haven't decayed yet, the rate of decay is faster because there's more particles that could decay. When there's less particles that could decay, therefore the rate of decay is slower. But what about those remaining, or those that it's decayed into, I should say? Well, you could talk about the size of the actual Guinness liquid, because what's happened there is as that head decays, as that head changes into the liquid, it will rise ever so slightly. So you get that idea of constant change between one increasing and one decreasing, and you can get that across the students really clearly with this. So that's a great model for radioactive decay. Another one is popcorn. So this one's really straightforward. You get a beaker, you put it on top of a Bunsen burner, a tripod and a gauze, bit of oil at the bottom of the beaker, put some popcorn kernels in there and heat it up. After a bit of time, once it gets hot, they'll start to pop. Now, if you put a lot of kernels in there, what you'll find is at the start, when there's a lot of kernels that could pop, you'll get lots of popping take place. Over time, as there's less kernels remaining, the rate of popping will decrease. And that again shows that exponential decay. The idea that when there's more kernels, there's more likely to be a pop, therefore the rate is higher because there's more kernels that could pop. So, I should say, when I say more likely to be a pop, that's an interesting phrase to consider. It's just there's more kernels that could pop, therefore more kernels will pop. So you've got to be really careful with the explanation with those with students. So what this model then does is it shows again the decrease in the number of kernels and the increase in the amount of popcorn. It's that constant change that's happening there that students struggle with that can be shown really clearly using these two examples. So if we come into evaluating these models, they model exponential decay really clearly. Okay, they make it a very simple process to show how one increases and one decreases, and they're very quick. They're both done within 5 to 6 minutes within a classroom, and they can be done straight after an explanation. They show that increase and decrease, but there's this whole idea of factors affecting change. So there's an issue with a couple of these models. So temperature is potentially an issue. Temperature has to be added to the popcorn model to make things happen. to make the popcorn kernels pop. And that could lead to a misconception there. So this is why we have to be careful when using model, because we know that nothing can affect the rate of radioactive decay in the sense of, obviously apart from the particle that actually is, because these models lend themselves to the fact that, well, hold on, if you increase the temperature, you're going to get more popping. Well, it doesn't work like that. So you have to be really careful when using models with our students. The great stuff about both these models, though, is they're quick, easy, they're not particularly messy, and they come straight after an explanation, and you're not having to let loose to the kids. So I hope you find both these models useful. Feel free to use them in conjunction with the dice experiment model, which I know is used widely, and I still use it occasionally if I'm looking at a data collection exercise. But both of these are great at getting that idea across once you've just gone through what we mean by exponential decay. Thank you very much, guys.